Newton's understanding of gravity was enough to permit us to travel from Earth to the Moon. But have you ever been thrown off balance by the endless hours spent wondering if our understanding of gravity is just the tip of a vast temporal iceberg? His insight is more than just a theory, it could be the key to unlocking deeper cosmic mysteries. The universe is far more complex and inspiring than we ever imagined. One of the most recent challenges to our perception of time comes from physicist Brian Cox. His groundbreaking theory could reshape how we understand the world. So, join us on an exciting journey through the passageways of time as we explore his bold ideas about how time truly works in the vast universe. Despite the progress we've made, many mysteries remain unsolved, especially those involving time and gravity, two forces essential to our existence. Imagine a reality where time moves unpredictably, speeding up or slowing down. Even gravity, the force that keeps us grounded, may not be what it seems. This brings us to Albert Einstein. His revolutionary theories of relativity gave us a new lens to view the universe. In the early 20th century, Einstein introduced the special and general theories of relativity, forever changing how we understand space and time. Special relativity, published in 1905, showed that the laws of physics apply to anyone not accelerating, no matter their motion. One of its most famous insights is time dilation, the idea that time slows down for objects moving at high speeds. A classic example is the light clock. If you're on a spaceship near light speed, a beam of light bouncing between mirrors travels farther in the eyes of an outside observer, making time appear slower on board. This is not just a thought experiment. Particle accelerators like the Large Hadron Collider send particles near light speed, where time dilation becomes a measurable reality. Special relativity also introduces length contraction. Objects in motion appear shorter along their direction of movement, and the iconic equation E=mc², showing that mass and energy are interchangeable. These ideas aren't abstract. They play a role in daily technology. GPS systems must account for time dilation caused by the high-speed motion of satellites. Without special relativity, your location could be way off. But Einstein didn't stop there. In 1915, he introduced general relativity, which redefined gravity. Instead of a simple pulling force between objects, gravity became the result of curved space-time. Massive objects like Earth bend the very fabric of space and time. Imagine a heavy ball placed on a stretched sheet, it creates a dip. Smaller objects roll toward that dip, mimicking gravity. This new model of gravity better explains the movements of planets and stars. It was confirmed dramatically during the 1919 solar eclipse, when Sir Arthur Eddington observed starlight bending around the Sun, just as Einstein predicted. General relativity also showed that gravity affects time. In areas of stronger gravity, time passes more slowly. Near a black hole, for example, a clock would tick much slower than it would far away. These ideas give rise to extraordinary phenomena like black holes and the event horizon, the point beyond which nothing can escape. Einstein even added a cosmological constant to his equations, believing the universe was static. Later, when it was found to be expanding, he called it his greatest blunder. Yet this idea laid the groundwork for the Big Bang theory. General relativity also predicted gravitational waves, ripples in spacetime caused by massive cosmic collisions. These were first detected in 2015, confirming Einstein's vision a century later. As Brian Cox explores, time may not be the unchanging, universal clock we once thought it to be. Instead, it's a fluid, shifting element of reality, intricately tied to motion, gravity, and the very fabric of space-time itself. This understanding suggests that time doesn't pass the same for everyone or everywhere. It stretches and contracts depending on how fast we move or how close we are to massive objects. Gravity, for instance, can slow time down, a concept proven by experiments with satellites and clocks in different gravitational fields. By rethinking time in this way, we might unlock answers to some of the universe's biggest mysteries. Could this new perspective help us understand the elusive dark matter and dark energy? Or the strange behavior of quantum particles? By looking at time not as a constant but as a dynamic part of the cosmos, we inch closer to solving the unknowns that have puzzled us for centuries. Stay with us here at Waves Discovery as we continue diving into these deep, mind-bending ideas, where science meets the strange, and the universe reveals its secrets one theory at a time.